And we keep streaming to the test server for some reason. Oh, that seems like we're on.
Yeah.
Oh, they're there. That looks like we are online. Okay. I can see
People
stuff.
can hear us.
I think people can keep. Yeah, we are. Okay, I got audio
Can
from it now.
Yep.
Hooray! Okay, it works. Thanks everyone for your patience. We had like a practice intro. So Zena, why don't we just jump into that?
Okay. Hello, everybody. Welcome to Starry Night Live. This is Zena.
And this is Matthew.
And our moderators for the night are Abby, Rohit, and Michael. And before we start and jump into our targets, we would like to acknowledge respectfully that we work on the shared unceded territory of the Tsleil-Waututh, Coquitlam, Squamish, Musqueam, and other Coast Salish peoples.
And we thought it was important to acknowledge that, given especially that tomorrow is a Day of Truth and Reconciliation in Canada, and there have been people on all of our lands across Canada that have been looking at stars far longer than we have. But in that tradition, we want to look to the skies ourselves tonight. And that's what we're doing. And thanks so much for joining us, and thank you for your patience. We have a cool list of targets today. We want to start with some that are nebulae. So nebulae are big clouds of dust and gas in space. The ones that we want to look at tonight, we have two of them in particular, one called the Swan Nebula and one called the Eagle Nebula. These are usually like summertime nebulae. They tend to be higher in the sky during the summertime. So we're just catching these right before they go beneath the horizon tonight. So that's why we put them on as our first target. So that's what we're going to do. Our camera is already pointing to space. Our telescope is open. We normally have a camera inside looking at the telescope as well. Right now you can see we've got two camera feeds that are outside looking at people walking around on the site. We normally have one inside. That one's not working right now, but we do have the camera attached to our telescope that is looking up into space. And so what we are going to do is start to image. So for those of us who have been around before, you might remember how this kind of works. We have our camera take images and basically stack them together, make like a sandwich of pictures. We call it a stack that's made of individual exposures. And we haven't done this in a long time. Zena, when's the last time we did Starry Nights live, virtual Starry Nights? I think it was during the pandemic even still.
Was that 2 years ago almost?
Yeah, it's been a long time. I was rusty. I was like, Zena was here while I was freaking out trying to get all the tech set up and put together, and I was like, I had no idea how to remember how to do anything clearly, which is why it took so long to get everything started up.
Well, I'm so glad that you figured it out, and we're all very proud of you
Oh,
because
thank you.
I
Uh,
would have not been able to contribute to any kind of tech problem solving.
Oh no, that's that. It was it was a pleasure having someone around, so I wasn't going nuts. Something else I want to share. It's really exciting. Okay, check this out. So over the last while, before we started this and virtual Starry Nights up again, some of you have been here in person, but we also got some really cool maintenance done on the telescope recently. I want to show you what it is. So
Yeah.
this is a picture here of the primary mirror on our telescope, and we had it cleaned. And it's been a long time coming since we had the main mirror on the telescope clean. So this is a before and after of the cleaning. I did not take this picture. It was done by a professional that was cleaning the mirrors, and you can see just how drastically different one side is from the other, the before and after. I think this is one of the first times the primary and secondary mirror on the camera was cleaned, but it has increased the performance of our telescope so much. And so before, if you remember in Starry Nights, we had to do a number of minutes of exposure before we started getting really clear images, even on really faint distant objects. And it's not like that anymore. Like, it collects so much more light so fast. So we're really glad that we had the telescope cleaned for this event.
Absolutely. It's a major difference between before cleaning and after cleaning.
All right, so let's give it a shot. Let's see what happens. I tried this earlier and it worked out. Of course, so did the stream. So we'll see what happens. So what we're going to do is the type of stack we're doing. This is a live stack on this object, and we're going to clear it and start over again from fresh. We should still be on target, and let's see what happens.
So we're looking at the
This should
Swan
be
Nebula.
Swan. We might have waited a little bit too long on
Oh,
Swan. It did show up earlier, but oh, we're not doing a long enough exposure. So what I'm going to do is I'm going to reload settings for our camera that tell the telescope to do a longer term exposure on our object. So before I had it just at like a few milliseconds. So what we're doing now is exposures of 20 seconds in length. And that's to basically like drink in light from the sky and getting all those photons. It's like a rain of light. And imagine that the telescope is like a bucket and we're collecting those images over the course of like 20, 30 seconds. And then we're layering them all together. And then we should see something in here. So do we have anything? We did earlier.
so to explain the metaphor, your bucket is the mirror.
That's
So
right.
our there's the three types of telescopes. The one type we have the reflector that uses mirrors, like our telescope, and there's the refractive that uses lenses, and the third type is the compound that uses both a mix of mirrors and lenses. So our bucket is the mirror, and the our observatory mirror is about the biggest one is about 70 centimeter, and all it's doing is collecting as much light as possible from the object, and then that light will be reflected either towards the camera or the eyepiece. But in this case, because we're seeing the objects through the eye of the camera, so it's going towards the camera.
So right now it's this actually is almost an overexposure. So we're going to change the point at which the telescope is trying to read the data. Basically, like the camera comes in, it doesn't know where the nebula is. So what we need to do is kind of focus. And what we're seeing here on the histogram, where you see my arrow is pointed, that's where like the main amount of light and information is coming from. So we basically want to center our what we call our histogram here, and you'll see this is already like the nebula is starting to come into field of view, and this is astonishing because this is only after like a few seconds of exposure, and we can already see so much like stuff here in the nebula, even after just a short period of time. Yeah, again, for anyone who remembered when we did Starry Nights before, getting a nebula like this would have taken, we would have been trying to expose for minutes and minutes and minutes already to get anything to look like this. But here we have the Omega Nebula. I'm going to play around with some of the colors here a little bit now.
Also known as the Swan Nebula,
Mm-hmm.
because apparently it looks like a swan.
And
Although I don't really see the swan, I see a whale. I don't know how many. I don't. I see a fish more than a swan
I'll get my
or the
green
whale.
down a little bit here. Oh, too much. Let's reset our color stream here.
But it's beautiful. It's bright red.
Take green down. You can tell I'm rusty at this. I used to be so much smoother with our color resets. Oh, that's not what I wanted to do. You're going to have to bear with me, folks. I'm a little bit rusty when it comes to navigating all this software. This is literally the first time that I've done any of this in a while. What do we know? What do we know about the Omega Nebula? What is this thing?
Well, the Omega Nebula is a stellar nebula. So there's two major types. So we have a planetary nebula, so that's a phase where a star is dying, or a type of star is dying. But a stellar nebula is a place where stars are being born.
There we go.
And we can tell, like, you can distinguish between a planetary and a stellar nebula just from the color and the shape. So stellar nebulas don't really have a shape. It creates all kinds of shapes. That's why, like, when some people, I guess, whoever the first person, Charles Messier, when he looked at the nebula, it looked like a swan. To me, it looks like a fish. I
Yeah,
don't
it kind
know.
of looks like a fish, doesn't it? Yeah, there's like this is 6,000 light years away from Earth. So this light that we're looking through that just came to the telescope it's literally 6,000 light years old. So this before like the pyramids were built is when this light left, and it's one of the brightest and most massive star forming regions in our galaxy. So stars are literally being born in this cloud of dust and gas, but it's only about 1 million years old. You and I were talking about scale of time, like you were comparing stuff to like the age of the Earth, and we were saying like 1 million years might seem like a long time to us, but it's certainly not as long to say like our solar system.
No, absolutely. Earth is only approximately 4 billion years old.
Yeah, so a million years is like a breath.
Exactly.
Yeah.
And another, just to mention, another distinction for a stellar nebula. So stellar nebula will be red or more on the red pink shade, while planetary, they'll have multiple colors. And the reason why we see the red color shades in stellar nebula or starburst nebula is because it's because of the gases that's there. Every gas in the universe will have a certain color, and hydrogen is usually red.
Yeah, I
So we
noticed
made
that too. Like when I was, if I jam the red color up, like you could really start to see more of that sort of nebulosity there in the image.
and it makes sense because every star, when they're born, they start with hydrogen first, and then they go through. Then when you have nuclear fusion, then you go into the next elements.
Amazing. Apparently, this cluster is has at least 100 B-type stars inside. So Bs are like very large stars. They're not the largest in the universe, but they die very quickly. And so when these stars are being churned out of a nebula like this, some of them are dying while others are still being born. So the largest ones that are most massive, they burn through their fuel really quickly, and they can destroy the nebula. The explosions from those can distort and change the nebula, but also the explosions can trigger more star formation within the cloud. So as one star is dying, that the explosion will ripple through the cloud and form more stars at the same time.
And you know what? That maybe it also changes the shape of the nebula too.
Likely it does. In fact, there was speculation, the next target that we were going to look at, there was speculation that it might already have been destroyed by a supernova, but there's more recent evidence that says it's not. But shall we move on to the next nebula before it drips over the horizon?
Sure.
All right, let's do it. So we're going to move the telescope. We have this handy piece of software that has a whole map of the night sky on it. This software is called The Sky, and literally all we have to do is punch up our target, and we can go to where do we got to go? The Sky X. So this is the Swan Nebula, or Omega Nebula, as people pointed out in the chat. The one we're going to go to now is called the Eagle Nebula. And this nebula is
not that far off. It's like its neighbor.
Yeah, sort of in the same direction. We're basically all right here. So if you look at our chart right now, there's a map of space that we're looking at. This sort of darker area outside of the shaded gray is where the hole in the dome is. So this is the dome roof that the telescope is looking at. And if you look at this haze, kind of this passing vertically, this is the galaxy. So that's the Milky Way. And these nebula are toward the center of the galaxy. This is the center of the galaxy down here. And the reason why we tend to see these star-forming nebula, like the one we're looking at right now, is that stars are born along the disk of the nebula where these spiral arms are. There's all the raw material that these nebulae are made from is making stars. So it makes sense why they are in this direction. They just tend to be a little bit higher in the summer months, which is why we're about to lose them over the horizon here. So on that note, we should probably move the telescope over.
And vice versa is true. So the further away you are, the further away from the edge of the galaxy and more towards the center, you get to see more of the older stars, the dying stars.
Yes, yeah.
Red giant, and eventually the closer you get to the center, where you have the black hole. Oh, black holes.
Or black holes, plural. Yeah. Ominous. Okay, so we moved the telescope. Now, while we were moving, there may have been some exposure going on. So I'm actually going to clear this one because we might have some motion captured in that one where it'll smear across. In fact, one of the things that's really important to the telescope as it's imaging is that it's always pointed in the same place in the sky. And this is the tracking of the telescope. So right now, this graph that shows the yellow and purple lines here that are jumping around, this shows the tracking of the telescope, the minute vibrations that the telescope is experiencing in order to keep itself pointed in one direction. And so this allows us to remain fixed on one place in the sky and track it so that it doesn't move out of our field of view. Again, it's not moving. We are, because the Earth is turning. It took us thousands of years to figure that out, by the way. All right.
Nice.
And let's see what we got.
I wonder that vibration, because this also measures the vibration of the ground. So if for people who go do it in person, when we do a test where we actually make a jump or make a clap, and then you'll see like larger spikes, just to show how sensitive this software is.
Yeah, it's one of the favorite things of kids to do when we have them come in, make a jump, and have it have the shake show up.
I wonder if if they use this to measure presence of earthquakes.
I bet you we could. I mean, one time there was some weirdness going on with the observatory, and we wondered if it had suffered an earthquake. Oh, look at that! Amazing. Okay, here. Stretch this out. Yes. Oh, that's cool.
Our eagle?
Yeah, this is the Eagle Nebula. Let's pull that green down a little bit more. Oh, tap back. Oh, actually look pretty cool. Oh, check that out. Amazing. I'm going to zoom in on one of the features here.
Yes, that would be great.
Oh, wrong direction. Let's go this way. Dun, dun, dun. Okay, so you see these sort of pillars here that are part of the Eagle Nebula here that I'm circling around. Let's drop a little bit more red so it's a bit clearer. There we go. These are called the Pillars of Creation, and it's another active star-forming region in our galaxy. This is about 8,000 light years away. These spires that we're seeing are light years and light years long. So trillions and trillions and trillions of kilometers. And we think it's about 1 to 2 million years old as well. But it was suspected that in this area where we're seeing this, there could have been a supernova explosion that had already destroyed those pillars and that they were no longer there anymore. But the reason why I wanted to zoom in on this is one of the most famous regions that have been imaged by the Hubble Space Telescope, which is really cool. And I've got one of the pictures here because that region has also been re-imaged now by the James Webb Space Telescope, and I have both images side by side. So this is actually them here. And the significance of this is that the Hubble Space Telescope, you can tell how much clearer that is than our telescope. But in fairness, that telescope was billions of dollars more than ours was. In this image on the left,
Yeah.
you don't see as many stars, whereas on the right you do. And that's because the Webb telescope sees in the same spectrum of light that ours does, which is optical light. Whereas on the right, this is the Webb telescope taking that picture, and Webb sees in infrared. So one of the advantages of this new telescope we have out there in space is that it can see inside of these clouds of dust and gas that otherwise it's difficult for us to be able to see into. So we begin to see stars at this earlier phase of their creation, which is really, really cool. So we're starting to learn even more about star formation by imaging these areas. What do you think, Zena? Do you think in a few billion years there'll be civilizations emerging from one of these stars doing what we're doing now, their own starry nights?
Oh, I'm sure. If you believe in the parallel universe or the universe, I'm sure.
Yeah, why not?
Like literally today, a kid came to me. He was showing me he was also showing me something to do with space, like a TikTok video, and it was about the multi-universe, and he looked at me. He's
That's
like,
awesome.
"You believe in this?" So he's like, "Somewhere out there, you and me exist. We're doing the exact same thing at the same time," as in like showing me that video.
That video somewhere else, right? Yeah, I did a presentation on the multiverse once, and we were talking about like almost like the fear of missing out on a different version of you that lived in another universe. I was like, I think all of our goal, because we don't know if the multiverse exists, but all of our goal should be to make the other versions jealous of what we're doing in this universe. And,
It's nice.
yeah. Someone asked about binning in the chat. And binning is what we call a combination of pixels. So think of it like this. When things are dim in an image, what we can do is combine pixels together to make a brighter pixel. So you take a couple pixels that are neighboring. Pixels are the sensors that are the tiny little individual sensors that are part of your camera that are picking up these drops from space. And we can add them together, adjacent pixels, to make something a little bit brighter, especially if it's bright or dim rather. The trade-off though is that you lose resolution, and then at some of these nebulae are not as sharp that way. But now that our mirror has been cleaned and we have more light coming in, we might be able to change binning. So I've dropped it down so we're now at full possible resolution, and let's see if the Eagle Nebula looks any better that way.
Yes,
Might get
so
some more sharpness out of it.
Brightness for details
That's right.
and
But
vice versa.
we might not need to do that trade-off. So let's see. It is a bit fuzzier. It's possible that I don't have a dark frame loaded for this version.
You know what I'm impressed about this nebula is that it has just that nebula in that region. There are about 8,000 stars.
Isn't
And
that
I'm
amazing?
I'm assuming those are all newborn stars.
Yeah, yeah. Just and that's why I think it's so neat to think about what might come from that civilization. Yeah. So this image is a little bit noisier than I was hoping. So we have something called a dark frame that helps to basically it's like an image that maps the noise inside of the camera and it's subtracted from each of the images we take. And this dark frame might not be working quite as well as we hoped. We also might be lower on the horizon than I want at this point, but
I think that's what it is because we've imaged this nebula before and it looked great. So I think maybe you're right. Maybe it is already going down the horizon.
let's zoom in on it though and
Already
see how
down
much
below the
sharper.
horizon.
Yeah, let's zoom in and see. You know what? It's not quite. I think the previous version might have looked a bit better. But good question on that one. Um, Matt in the parallel universe controlling JWST instead. I wish. Wouldn't that be amazing? That would be. Wouldn't that be amazing? I know. In the meantime, I still get to share the pictures, and that's pretty cool. What are we off to next, Zena? What else do we want to look at here?
We have we can switch to an open cluster.
Yeah, you want to do that? Okay.
Yeah, so we could do NGC 869 double cluster.
Okay, let's do it.
Okay,
Abby
right.
mentions here whoever's doing Starry Nights in the parallel universe. I'm pretty sure there's one Vancouver that's not raining. It's probably only one of a few million universes, though. I wonder. Oh god. Okay, let's see.
Okay.
Try the denoiser and enhancement tab. Joanna says. Okay, we might try that if we end up if we're noisy on one of the other tabs here. Okay, we're looking at NGC. We want to do 869, so one of the double cluster.
But yeah.
Some people had asked in the chat, how come we can't be there in person? And normally we are. So normally 3 days of the week we're still going to be doing in-person Starry Nights. But we had a number of requests from people to do Starry Nights virtually again, just because of the audience that we had created during the pandemic from people who couldn't tune in. In fact, one of my former housemates, Tom, I don't know if he's still here, is just tuned in right now all the way from Toronto, or from Ontario at least, and that's pretty amazing. So thank you for that. These are people that are participating that otherwise wouldn't be able to.
And it's also easier for parents. Like a lot of parents who have kids and bedtime, this is a lot easier for them to participate.
All right,
Yeah.
so telescopes moving over. We're moving to one of two clusters that are near each other in a feature called the double cluster.
I'm actually excited to see that double cluster.
I am too, actually. Yeah, I find like I don't think of open clusters as one of my go-tos um, for targets, but they are neat.
Yeah, well, I think when you think about this, if you just think about the science behind an open cluster versus a globular cluster, then I find it mind blowing. Because with open cluster, so open cluster are much younger, much younger than a globular cluster, and you can tell from the types of stars that exist in each type. So with open cluster, because it's younger, we should see more of the blue stars. So blue stars are young and very hot, while old stars are red and cold.
Yeah, and in a way, we're taking like a step forward from where we just did in stellar evolutionary history, right? Because we started with a gas cloud that's giving birth to stars, and this is kind of the next step of them, right?
Exactly. Oh, you gave it away.
Oh, I'm sorry. I'm sorry.
No, I'm joking. No, it's good. Now they know what. That's actually amazing. So now they know the direction we're going. So we're starting from the origin of the stars and then going further and further into the end.
Yeah, so basically what happens, you can think of an open cluster as like birds that are now leaving the nest. So they form inside of one of these big gas clouds like the ones that we were looking at earlier about the Eagle Nebula and the Swan Nebula. And once enough of those stars form, their combined energy and their explosions from their supernovae begin to clear that gas away. And then you get an open cluster. So this is basically a cluster of newborn stars out there in the galaxy.
Yes, and Eventually, an open cluster will turn into a globular cluster, which we'll show you later in the night, hopefully. I guess a cluster, just from the term cluster, means it's just a cluster. It's just literally a cluster of stars, and the ideas of the stars are gravitating towards each other. So something is making them get closer and closer towards a certain center. And I don't think we know what that center is yet. There are some theories, maybe it's a black hole, or maybe it's just the star itself. It just one pulls the other, and
Yeah,
eventually.
yeah, and if the cluster is loose enough, like this one, so typically of newborn stars, what will happen is they eventually will separate from each other and stir off into the galaxy and find their own way, which is what happened with ours. So I think we have found at least one star, if I recall correctly, that was part of the original cluster that we were born from, which is pretty amazing. Let's see what we can get here at this one.
We're actually a very unique solar system. We're a special solar system.
It's the only one where I can guarantee that you and I are doing Starry Nights.
Sure, sure. I was gonna say that majority of the stars in the universe, they're in binary or in some form of a system.
Yes, of course. Yeah,
And and most it's so I was gonna say like having a solar system with just one star is very unique in our universe. That's
absolutely.
what I thought. We are very special.
This is called NGC 869. It's one of two clusters that are near each other, also known as the double cluster. So this is one of them. It is 7,460 light years away from Earth, but it's also part of something called the Perseus OB1 Association. And what those are, OB1 associations are groups from 10 to 100 very large stars that have formed within star clusters or inside of those clouds of gas, like the ones that we were looking at. And so this one is they tend to be named after the arm of the galaxy that they belong to. So this one belongs to the Perseus arm of the Milky Way galaxy. Ours is the Sagittarius arm, and the majority of all stars are formed next to an association of giant stars like this that are kind of drifting by each other throughout the galaxy. So we're looking at these very young stars starting to take flight into the galaxy, kind of traveling with each other as they spread out into space. Only about 14 million years old. So,
Which is very young. This is considered very young in space terms.
Oh yeah,
A very young target because Earth itself is 4.5 billion years old.
it's a breath. And our sun is the same age. So to think that there are some stars out there that have died after only a few million years is astonishing. But of course, we need that to happen because as stars are close together like this, as they're forming, when those big stars blow up, they are seeding the solar systems around them with the heavier elements that we need for life. So if there weren't big stars that were a part of our group of stars that had blown up early, we wouldn't have the material that makes like the calcium in your bones or the iron in your blood or the oxygen that we're breathing.
Or the nitrogen in your DNA.
Yeah, exactly. Yeah.
Material.
The carbon.
Your...
Yeah. So all that stuff needs to get out. So stars are cooking up life. It just that happens to be that we're the only place in the universe we know of so far where those materials have assembled themselves in a way that can walk and talk and dream and look through telescopes and know where they came from. And that's pretty astonishing.
Totally.
All right, where are we off to next?
Originating from a supernova.
Yeah, actually, do you want to do a planetary nebula first?
Before going to
the galaxies? Is that what you want to do?
Yeah, we can do that. Yeah.
Yeah. Okay.
Sure. So you want to do the Ring Nebula?
Sure. Yeah. These are stars being born. Let's look at a star that's on its way out.
Okay. So I can just give some facts about planetary.
Please,
talked about planetary nebula in general. So we've talked about stellar nebula. The second type of nebula we have, it's called planetary. And for the longest time, I was just confused about the term planetary. I don't know why I was trying to figure out why is it called planetary? Why couldn't they just call it a death nebula or a dying nebula?
Death nebula.
Why planetary? And then when I was looking into it, so I believe it was Charles Messier, the astronomer, the French astronomer, when he looked at nebula or planetary nebula, it looked like a planet. Gosh, so creative. So I just decided to call it planetary from the word planet because they have the round shape with the planetary nebula. So that's the origin of the name or where it came from. But planetary nebula, so if you have stars like our sun, so our sun is not very massive. So stars that are not very massive like our sun, they will go do nuclear fusion and they start with hydrogen and then they keep going until they get to carbon. So once they get to carbon, then you'll end up with what's called a carbon core, and the star has already became what's called a white dwarf. So our sun is destined to turn into a white dwarf. So all these colorful gases and dust that you see in the nebula, this is all the gases that the star is shedding. So usually we see the red color first because that represents hydrogen, and then you see all the different colors that represents different gases, and for the ring nebula itself, we see more of the blue color, and blue, I believe it's oxygen, or representative of oxygen gas. So I really enjoy the science behind the different colors of the nebula.
Yeah, at the other place I work, the H.R. McMillan Space Center, we have a show that's literally called The Color of Fire. And it's all about how just using color we can determine what something is from so far away. I mean, that's a majority of how we know what stuff's made of out there in space.
Oh, yeah, absolutely. And talking about white dwarf, so I believe most people know that diamond is simply chains of carbon. So white dwarf is just because white dwarf is just a carbon core. So that's you can think of it as diamond in the night sky or diamond in space. So our sun is destined to turn into a giant diamond. I find that poetic, that thought.
That is poetic. Yeah, this is what will look like in the future. In fact, I believe, and Dr. Joanna Wu is in the stream right now, I can confirm, but I'm pretty sure the central bright point that we see in this nebula actually is the white dwarf in the center, the core of the star that's now been shed, or for the first time is visible out there in the universe, which I think is pretty astonishing.
And the ring nebula itself, that white dwarf, I believe, is a similar size to our sun.
Yes. Yes.
Or was a similar size.
Yeah, and so a star that would create that. So we'll look like this sort of in the future. Kind of an interesting note that I wrote down from this one is that the ring nebula, if you looked at the shape of it, it's called a prolate spheroid, which means it's kind of like an egg shape in space. Kind of circular-ish, or spherical, but elongated on opposite sides. And the center of a white dwarf, like, I don't know if we give white dwarfs enough credit. They're like 100,000 degrees. Like, these things are really, really hot. Very dense. Not nearly as dense as other collapsed stars, but very, very dense out there in space. So this is what we'll look like to, some other future civilization in 5 billion years or so. The ring nebula itself is over a light year across already, and it's probably been expanding for about 2,000 years. So that star has died in the recent past. I wonder if anyone was there.
You know what's interesting? So if we were to live, or maybe even in wherever that planet, that ring nebula is, or even where we are, we actually don't get to see the nebula. So if we were to go where that nebula is, we don't actually get to actually experience the colors. You can only see the nebula and the colors from far away.
And is that because of density? It's not nearly as dense as when you're inside of it as when you would be far away?
So. That's probably. So we could be living. So if somebody was living on the other side and looking towards us, they might see us inside a nebula, but we don't see it. We don't experience that.
It's not like in movies where you can hide in the nebula and it's like a big giant cloud around you. It's probably not quite like that. Nebula are far more diffuse than I think we would say. Although I will say this, Zena, if you were standing on a planet in that solar system when the sun expanded into a red giant and ate you, you would definitely see that.
After 8 minutes.
Yeah, if the sun exploded. Yeah, exactly. But
it takes 8 minutes for the light from the sun to get here.
So
we'll see it after 8 minutes.
Yeah.
But the truth is, we would not even see that because we would already be dead.
Oh yeah, it would kill us. Yeah, that's if it exploded. But when the sun does expand slowly into a red giant over eons of time, you would be able to see that from the Earth's surface. It's just that you wouldn't want to be on the Earth at that point. When it finally consumes you, that would be a bad day for planet Earth.
You know
Actually,
something? Oh yeah, go ahead.
no, I was gonna say that's how Doctor Who hooked me. I don't know if there's any Doctor Who fans out there in the chat, but where it finally got me, where the second episode of Doctor Who, when it rebooted, I was like, if I had a time travel machine, what I would want to do is go and see the day when the Earth is finally consumed by the sun, and that's literally the second episode of the show. And I was like, yes, Doctor Who for the win.
You know, I find like the most mind-blowing aspect when it comes to space or astronomy in general is the aspect of time.
Oh
Like,
yeah,
because whenever we look into any target or any celestial object in the universe, you're always looking at it happening in the past. So all these, for example, blue stars, we could be just seeing the ghost. We're looking just at the ghost of those stars that might have already just exploded or turned into a supernova.
yeah, literally looking at the universe's memories.
Literally,
Yeah,
yes.
it's amazing. Yeah, I think it's astonishing. That's another reason, again, time travel, why we have a TARDIS, the Doctor's time machine, inside the planetarium or the observatory. If anyone's been to the observatory, you will have seen that we have one of the Doctor's time machines in there. This is another planetary nebula. This one is the Dumbbell Nebula, so another dying star out there in space. A little bit larger in the field of view than we see from the Ring Nebula, so it's a little bit more prominent. We'll see a picture of it
Nice.
here in a moment. The
This
first,
one is in the small fox Vulpicula.
there we go.
Well, I don't know why. Whenever I read or think about the constellation, I think of Pokemon.
Oh yeah, yeah.
The Volpox,
Yeah.
the Volpox, they're very cute. It's just the way it sounds. I wonder that's where the inspiration for the name for the Pokemon
Oh,
came
maybe.
from.
Yeah, there's a lot of space-themed Pokemon, so that makes sense. I think that's probably definitely the case.
That's true.
So, can I tell you a story about Dumbbell and why it's close to my heart?
Oh yeah.
Okay.
Well, go for it.
So, when
That's actually one of the second one that I imaged, but yeah, go for it.
oh, that's cool. Yeah, so I have a similar story. So, now for those of you who've been up to the Trottier Observatory and the site and location where it is, it didn't always used to be there. So that facility was finished in 2015. The construction was begun in 2014. But in the years prior to that, it was just a big open grass field. Now, the SFU professor who spearheaded the whole initiative, Dr. Howard Trottier, he used to do starry nights on that field, but just with his own personal telescope. And so he would bring students out onto the field and they would go and like look at space and stuff. Anyways, one night, he asked me, he's like, hey, Matt, because him and I had met, he knew I was a big space keener and wanted to be involved in the observatory. But anyone who knows Howard, he sounds more like this. He's like, hey, Matt, do you want to do astrophotography tonight? And I was like, yeah, sure. So he invited me out and we stayed with his little telescope out till like 4 o'clock in the morning, imaging the Dumbbell Nebula. This is what we did. And
Awesome.
it was so great. I don't know whatever happened to those photos, but I was just happy to hang out with Howard and know that, in the future, in the same spot where we were sitting on grass, there was going to be an observatory. And now there is. And on the way home, I bumped into the biggest bear, big giant black bear on residence, but he didn't care. He's just eating garbage.
That's nice. I think one of my stories with animals, because I did when I was doing my master's at SFU, people who do their masters probably in science, you don't really have a life. You don't have sleep time. You just have to do the experiment until you can't leave. So a lot of times I had to stay till the morning to finish up my experiment because that's just how it is.
Yep.
That actually, because I spend a lot of time at SFU and the observatory, and so Howard would sometimes like send me a message, tell me, can you go image this? Can you go open the observatory? So I actually spend a lot of time between my lab and between doing imaging at the observatory. So it was very productive. I was very productive doing two things. Because sometimes I can have something waiting. So sometimes I have an experiment and I have to wait 3 hours before I do the next step. So during those 3 hours, I will go to the observatory and do some imaging. So one of those times when it was time for me to go home, to actually go to sleep, I ran into this coyote and he was between me and the car and it was just me. I was the only one in the parking lot. I didn't know what to do and the coyote would not move. and we were just staring at each other. It was like a staring contest. I wasn't sure what him to do. He was just standing in front of the car, and I don't know, do I approach it? Do I just wait? And there was no one around. It was pitch dark, so I decided, you know what? I opened my phone and I recorded myself because I figured, you know, I need to go. I was so tired. I'm just gonna go approach that coyote. Whatever happens, I have it recorded in case my family asks what happens to me. You know.
Yep.
Then, as I start walking, the coyote was still there. He didn't move, but then the coyote moved and it went into somewhere into the bushes. And then I realized the coyote was actually trying to distract me to let its family
Oh,
cross.
okay. Yeah.
I didn't realize there was more of them because which it kind of was kind of clever. I guess coyotes are clever like foxes.
Oh, I bet. Yeah.
It was like, oh, okay, it was just trying to keep me in check and make sure I don't pay attention to its family so they could go into safety.
Yeah.
I was like, okay, that's awesome. As long as you don't come after me.
Uh,
So yeah. That looks amazing.
yeah, here we go. And you were mentioning the colors in the nebula. You can definitely see the red out there, that hydrogen that's being expelled in the outer envelope. This one is about 1,360 light years away. It's also a prolate spheroid, for those of you who are geometry nerds. Is that a thing? There's a lot of knots in the central region that have been observed, so twisted kind of winds coming out from that central white dwarf star. And this one's about 10,000 years old. So this is an older nebula from a star that died ancient time as far as we're concerned, but in the lifetime of a star, not very long ago.
And I also this nebula itself is actually one of the brightest one in the northern hemisphere, probably the third brightest, so you can see it with binoculars.
Awesome.
In a clear night, of course.
Yeah.
Maybe not Vancouver.
Yeah, maybe. I don't. It depends on the binoculars, I guess. Now we had talked about where ancient stars have gathered together and have maybe even formed together. I think is one of the hypotheses around globular clusters. Do we want to go to a globular cluster?
Yes, of course.
All right, let's do it. It's actually one of my favorite things to look at. So the one that we're going to go to.
Actually, the one we're gonna do M13 is actually the very first target that I imaged with Howard.
Oh, neat! Wow, yeah, that's awesome.
It's like, so this one holds a special place in my heart with regards to the Trottier Observatory.
Yeah.
Imaging experience.
I miss Howard. I haven't seen him in so long.
Yeah.
I saw him randomly walking down the road by the planetarium the other day, and I was like, yelling at the car door, and he was like, what's going on? But every once in a while, I had a Howard sighting.
Oh, cool. That's awesome. I don't know. He's probably just doing imaging with his observatory in LA. It's in LA, I believe.
It's in California, but definitely outside of LA because it's very bright. But he's there. There was a question: is the hydrogen being at the edge related to the fact that hydrogen has a lower mass? And yes, that is true. So the atoms are being accelerated, just like force equals mass times acceleration. And so as they're being expelled from the star, what? You got a chance to catch up with them? Look at you! Look at this! Look at all these stars, Xena. This is amazing. Globular clusters, so cool.
He was on campus today?
What?
That's a cool. Oh my God, look at the glob. That's amazing. Look at the glob.
Look at this. Fantastic.
Amazing.
Again, I can't believe how quickly the results are coming out of the telescope since the cleaning. This is amazing.
So clear.
So clear.
You don't even see the dust bunnies as obvious.
Yeah, they are there sometimes, but
some, like in the past, it's very clear. Like you can't help but look at them, and even when I try to edit, it's hard to get rid of those dust bunnies.
Yes, yeah.
But at least with this one, like you don't even notice them. No, they're not as obvious. Actually, so globular clusters are very, very interesting. Even if you were to go observing with your binoculars, they're nice to look at. And with M13 in particular, so M13 is, interestingly, it says that we would always been saying that it was discovered or cataloged by Charles Messier, but actually, it was actually discovered by Edmund Halley. So the guy who discovered Halley's Comet.
Nice.
So I did not know that. I learned that very, very recently. So Edmund Halley was the first one to observe it, but then Charles Messier is the first one to catalog it or document it.
Yeah, it's incredible. Like there could be hundreds of thousands of stars in a cluster like this. We're not sure what the origin of these are, but the leading hypothesis is that they might form similar to an open cluster, but there are so many stars that they just never leave each other, so they're gravitationally bound, and they might be the result of galactic collisions, especially
Yeah.
when the galaxy was very young. So, at the Milky
Yes.
Way, yeah. The Milky Way, has it's a product of collision with other galaxies, and when that happens, there are massive starbursts
Yes.
that occur, and these big knots of stars, far larger than typical star forming regions that we've imaged, will form, and the stars are now held together by gravity.
Yeah. So also globular clusters, they are one of the oldest targets in the universe. So globular clusters are close to the age of the universe. This one in particular is about 12 billion years old.
Ancient.
To put into perspective, our universe is 13.8 billion years old. And what you mentioned something about the star collision, because with globular cluster you would, because how old they are, you would think most of the stars are red giants or red supergiants or all the old stars. You won't see any of the young blue stars, but you still see some of them. Like if you were to do the imaging, like you probably would note, like if you get more stars, you probably would notice there's some blue stars in there.
Mm-hmm.
And a lot of astronomers were wondering, why do we see blue stars in a very, very old target? And one of the theories is the stellar collision. So they think from stellar collision that could create new stars, or a way to create new young stars.
Yeah, which is awesome. Kurt asks a question here: shouldn't M13 be a galaxy? That's a good question. There actually is another, the largest cluster that we know of in our galaxy is called Omega Centauri. And it's enormous. And it's possible that something like that might be the core left over of a dwarf galaxy that's been absorbed by another galaxy. So that's possible as well. There are a few hundred of these orbiting around the Milky Way. They kind of orbit around the core of the galaxy, and we've observed them in other galaxies as well, so they know that they're there. This is one of the few places where we've done something called METI. Not SETI, the search for extraterrestrial intelligence, but METI, which is messaging extraterrestrial intelligence. So we once beamed a message to this globular cluster, I believe in 1976, 74. What are my notes here? What did they say? 1974. It was called the Arecibo signal. So it was sent from the Arecibo telescope, rest in peace, and it was sent to this cluster. It won't reach for 25 to 30,000 years because that's how far away it is. But it was kind of an interesting academic exercise, and there are some suggestions that maybe, if you're a super advanced civilization, this might be a good place to take up, because if there were planets in clusters like these, and so far we have no evidence that there is, but if there were, you'd be able to communicate between solar systems in like a few weeks or a few days rather than years, because in our part of the galaxy, stars are typically light years apart, but in a cluster like this, it could be light days or light weeks. So this might be a place to take up, but the sky would just be astonishing. The stars are so close together. It'd be giant glowing orbs like everywhere.
So they probably would never even experience nighttime. So they will have to have some sort of different technology, or I don't know, maybe they would have different types of eyes that could see into the night sky.
Fancy.
Not like, because for us, if we were to live there, we would not be able to see the night sky and the stars.
Yeah, you're right. In fact, there's a story that's written by science fiction writer Isaac Asimov, and it's called Nightfall, and it's about a civilization that grows up in a globular cluster, and their whole civilization is kind of stunted in terms of science and technology because they can't see the rest of space because it's too bright in their cluster. So much of our own science is driven by our view of the night sky, but what happens is there happens to be an alignment of moons that block out some of the closer stars, like an eclipse that's like a total fluke, maybe 1 in 10,000 or a million years or whatever. And for the first time, that civilization is able to see the rest of space. And to be honest, I can't tell you what happens because I've never read the story after that. I just know the premise. So that's what I should check out.
I have a prompt for you.
Okay.
If you were to pick a place to live in space other than our own, either to live in a globular cluster, a civilization within a globular cluster, or a civilization within a merging galaxy.
Okay.
Or a binary system.
Ooh, These are all fancy. I might go with globular cluster. That might be neat, or maybe somewhere near the center of the galaxy, if it's possible. By the way, folks, like when we are looking at these images right now, we're looking with them at something called the ZWO. It's our kind of like it's like a super fancy space webcam, but it's not our primary imaging camera. So when we look at something very briefly, we can get kind of like a lower resolution, quick colors so we can show you as the public. But we've imaged this target with our main camera, and this is what it looks like through the main camera. Look at the density of the stars that show up in this picture. That is astonishing. So this is one of the first images that was taken with the telescope, and this is after a few hours of exposure and lots of processing time. And this image was done by Dr. Howard Trottier, and I would be remiss to point out, because he points it out every time, he's very proud of the fact that in the upper right-hand corner of the image, he managed to process and find a distant background galaxy that's in this picture as well. So it's kind of like an edge-on galaxy that's there in the distance. I don't ask me the name of this galaxy that's in the distance in this corner of the picture, but it is there, and he was very proud of it, so I'm going to make sure to point it out because it's kind of neat. Distant galaxy there in the background.
You know, globular clusters have very significant impact in terms of knowledge of astronomy that we have right now. So if you probably remember Shapley. So he was one of the astronomers who studied globular clusters, and he used them to figure out where the solar system within our galaxy.
Oh, so, cool. Yeah.
For the longest time, we believed we were in the center of the galaxy.
Yeah.
And that our galaxy is our universe. Until, Shapley came up with the theory that we are not in the center. We are more on the edge. We're actually far, far away from the center of the galaxy. And he was able to come up with that theory from studying globular cluster, because how they are distributed in our night sky. So if we are in the center of the galaxy, then the globular cluster would be distributed evenly in our night sky, but that was not the case.
Science!
And no one believed him.
I know. Proving that we're not at the center of anything since 1609.
I know. And then until Edwin Hubble came. And that was in 1923. No, 1925. So that's not even 100 years ago. That's 98 years ago. He came and proved Shapley's theory that there are millions of galaxies out there beside the Milky Way. And we're just one out of millions of galaxies that exist. And we are nowhere near the center.
Speaking of which, we're trying to get an image of a galaxy now. So this is Bode's galaxy, and I'm looking at the first image. Now, this target's tough because it's toward the Big Dipper, and the Big Dipper is over top of the academic quadrangle, one of the main buildings at SFU, and it's sort of bright, and there's a lot of trees in that direction, so I don't think we're going to get a good image of this.
To try. Both galaxies are really nice looking galaxy.
Yeah, the problem is that, okay, so how this works, the computer needs to stack images using stars in the background, and there's not a lot of stars coming out on this picture. There is some data in here.
There's also a Cigar Galaxy, its neighbor.
Yeah, we might be able to do that instead. Let's see, what did we get out of here?
I like Edge-on Galaxy.
If I bring down the red... no, I don't think we're going to get this galaxy. Nope. Okay. That might be... we might be able to wash. Do you want to do Pinwheel? Because then we can talk about that supernova. Do you want to do that?
Sure, let's do that.
Let's do that. Okay. Bode's galaxy is one of my favorite targets. It is beautiful, but it's always sort of in an inconvenient place in the sky. So we're going to check a different one instead.
How far away is the Bode?
It's got to be. It's probably about. Actually, I'm going to list down 20 million light years. Let me just do a quick look. Sorry, it's half that distance. 11 million.
About 12 million light years. About 12, yeah.
No big deal.
I was trying to think about a galaxy that's 60 million light years away. Because I was just thinking if there is a civilization that lives on that galaxy and they're looking towards us, as in like they're observing us, they would be seeing the dinosaurs. They wouldn't be seeing us.
Yeah, if you had a powerful enough telescope, yeah, for sure you could do it.
Or they'll be observing, or maybe they will see the asteroid that killed the dinosaurs.
Yep. Wouldn't that be something to see? Wow, what a cataclysmic event. My goodness.
Yeah.
Okay, if we don't get a photo of this one, we have one saved as backup because something really cool happened with this galaxy back in May. Is that we observed a supernova.
Yes. Yes. So the Pinwheel Galaxy. So that's about 21 million light years away. And it's in the Big Dipper or Ursa Major. And the type of, for those of you, I've ran into supernova nerds. I don't know what to call them, or they're really into knowing supernovas. So one of the questions I get from them is, there are different types of supernova. What's the different types, or how are they distinguished? So this one in the Pinwheel Galaxy, it's type 2 supernova, and type 2 supernova indicates that it's just a star it's a super red giant that it's at the end of its cycle, and then it just goes into the explosion, which is the supernova. So when a star gets to iron or fusing iron, it becomes very unstable, and where it can hold its core, and then it just goes into kaboom, supernova. And the type 1 supernova, it's in a binary system. So that's when you have two stars orbiting around each other, and when it just gets to a point where it's not stable and it can hold the rotation, then it will also go into explosion or a supernova.
Look, it's there. We can see it. Amazing.
The supernova or the galaxy?
The galaxy, yeah. We're actually able to see it's starting to come into view now, but you can see the central core. So right here where I'm moving my mouse arrow, that's the core of the galaxy. Galaxies tend to form from kind of the inside out. So the middle of the galaxy has the older stars that are kind of reddish in color, and the outside of the galaxy tends to have the younger stars where you have more of a bluish tinge. And this one, the way that I've had to stretch this image, I got to kind of dig deeper in the data. So Zita mentioned dust buddies. You can see one of them here. That's what this circle is. That's the dust buddy there with the camera.
No. Right. Thanks a lot. You pointed it out. I didn't actually not notice it until you pointed it out.
Yeah, there it is. So that is one of the dust buddies. Unfortunately, that one is a little bit obvious.
That's obvious. But still, the galaxies looks amazing.
But yeah, that is there. Sorry if that you might have heard a bit of a scratch there as my microphone falling off the table. Okay, anyways, but yeah, you can see the spiral structure of the galaxy. This is called the pinwheel, and it is really, really cool because we're seeing it from the top down. Some galaxies we see from the edge on. Zena, you're mentioning that with like the cigar galaxy, whereas this one is that we're seeing it from kind of the top down. Now, what's cool about this is that we witnessed a supernova. I say we as humanity. We witnessed a supernova past May in this galaxy, and we imaged it. So we have a picture of when that supernova occurred. And so I'll bring it up.
It only took it 21 million years to get here.
That's right. Yeah, 21 million years ago, and then a couple days, and we managed to get it. So it is on, did I save it on the desktop? Here it is. And this is it. So that bright point here that I'm circling now with the mouse, that is the supernova. So that is not a star. So these other points that you see here, other points of light you see in the image, are stars in the foreground of our galaxy. So those are in the foreground. The arms are in the background, but that point of light is not in our galaxy. It's a star that has exploded in that distant galaxy. And if I bring up the image here, you'll see that we don't see that same associated bright point in the arms, and that's because after a few weeks, the supernova calms down and we don't see as bright an energy source from it anymore. But for a while, that star, that one exploded star, will outshine all the rest of the stars in the entire galaxy. It's brilliant flare at the end of its life, while maybe providing the material we need for life, or at least in this case, not us, but some other future civilization or life forms will need in some other distant
Well, it
galaxy.
probably already formed. We haven't received the light from it.
Oh yeah, maybe yeah. It depends, I guess. Yeah, I mean that material will have already spread into other solar systems. I think it took about 1 billion years or so for Earth to finally develop life on it. So who knows what the
That's
timelines are?
true. That's
But yeah, all that material spraying into space, so that maybe at some point it'll be
I
used
think
by some other
someone
biology.
in the chat was asking if there is a black hole in the center, or do we know if there's a black hole in the center?
Yeah, you know what? Off the top of my head, and maybe Joanna is Dr. Joanna Wu, who's in the chat here. She's the galaxy expert. I believe this might be one of the galaxies where there's speculation that
That
there is
doesn't have
not.
one.
Yeah, there's
Yeah.
not an observed supermassive black hole in the center. I also, it's funny, Zena. I pulled up this old photo, and that dust bunny is still there. So we should probably clean out that camera.
Doesn't want to go.
Yeah.
Oh
Uh,
yeah, it is there.
yeah.
Wow.
Good question from the chat. Said, what forms the spiral arms? And that's probably another good question for Dr. Joanna Wu, the galaxy expert. My understanding, though, is that the arms might actually be like density waves that ripple out through the galaxy as the galaxy is rotating. So it's like the arms are caused by the spiral rotation, but they're actually kind of like waves of stars themselves rippling through the galaxy. But Dr. Wu, if you're there and you want to speak to that point, because you're the galaxy expert,
From what
maybe
I
have a better answer than
know,
that.
because there's different types of galaxies, and each type is a different has represent a certain age. So the youngest galaxies are the one that are called the irregular, and they're mostly blue stars. And then as the stars age and you get more of the older stars, then they start to form that shape, and so you have all the older stars will go more towards the center, and the younger stars are born, or they will be more towards the arms.
Yes. Yeah. I've seen
Powerful.
simulations of that very thing. Um,
Yeah, and then also they also theorize that maybe it's galaxy collision could also form the spiral. So these are those two reasons. So the younger stars will be in the arms, and then the older stars will just go more and more towards the center, which kind of also makes sense. If you think about the oldest galaxies in the universe, those are the elliptical. And if you look at them, it's just from the shape. You don't see as many of the blue stars. You don't see any spirals. It's just an elliptical, and it's mostly just the older stars, the reddish oranges color.
yeah. It reminds me of a paper I read once where people were. I mean, it was just speculation. People were speculating like if there were an advanced alien civilization in a galaxy, where would you find it? And if they had evolved for a super long time on a planet or migrated somewhere, eventually they'd be either evolving on or migrating on star systems that eventually would make their way into the center of the galaxy. So that maybe that's where everyone is. They're like in the center of the galaxy. But the center of the galaxy also has like a bunch of supernovae and like black holes and radiation, and you're maybe close to a supermassive black hole. So maybe the center of the galaxy is not a good place to be. I don't know. That might not be. It might not be good. I've read speculation that even galaxies themselves might have habitable zones where we find a habitable zone around a solar system where a planet needs to be the right temperature, but maybe solar systems have to be in a certain part of the galaxy in order to be habitable as well. Dr. Joanna Wu says that the most recent paper about M101 is that it's not that recent. The upper limit for a possible supermassive black hole is about a few million solar masses, so that's roughly the same as ours. So ours is 4 million, only 4 million solar masses.
Only 4 million.
You know what? We're getting close to the end of the night already. This one, every time we do this, we're always afraid of running out of things to talk about, which of course never happens. But we haven't looked at any planets yet, so maybe we should.
Yes. What do you want? Do you want Saturn or Jupiter? Well, actually, what's possible? That's a better
We
question.
might be able to do both, actually, if we do this. So if we play our cards right here.
Let's do Saturn first.
Okay,
I know
sounds good.
Saturn should be higher, and then because I think Jupiter falls after. I wonder if the moon's up as well.
Saturn is just so cool. I know so many people who went into whole careers of space just by seeing Saturn when they were like a kid through a telescope.
I know. Saturn, I would say it's my favorite, and I'm sure for many people. For me, because Saturn is the only planet that has that 3D shape. Because when you look at a planet, you just see the 2D. It's just like a circle.
Yeah.
But with Saturn itself, you actually see the 3D aspect with the ring. Which unfortunately, I learned that the rings are going to disappear one day,
Sadness.
but probably not within our lifetime. Probably within the next 100 million years or so. So they apparently because of the Saturn's gravity is pulling it towards the planet itself closer and closer, and eventually they will be gone and disappear. So look at that.
There we go.
Did you know that Saturn has a tilt similar to Earth? So the Earth tilt what creates the seasons, and Saturn has a similar tilt as Earth. So technically, if we could live on Saturn, there will be seasons. Except a season on Saturn will be 7 years.
That's so long.
So if you have allergies, you will not survive on Saturn during springtime.
Oh yeah, so what kind of pollen do you find on Saturn during the season?
Oh, maybe the diamond, because that's the other thing I learned, that it rains diamond on Saturn, which is so cool. How rich would I be?
How rich would you be?
I'll probably will be dead.
Or dead, yeah. If you're trying to harvest
dead more
Saturn
than rich over there.
So why I've heard this, that there's diamond rain on gas giant planets. So how does that happen?
So because they have lightning. So apparently with lightning, because it's 10,000 times more powerful than that on Earth, which is so crazy. So apparently that power from the lightning, it's when it's somehow when it interacts with methane, it creates this large clouds of soot, and when you have enough pressure, then it creates diamond.
Amazing.
Soot is just the ashes of carbon, and it makes sense. When you have chains of carbon, that creates diamond. So eventually, you have the lightning interacts with methane, and methane turns into diamond.
Isn't that astonishing to think that, like, diamond on Earth we think of as like this rare thing, but in the universe it's literally the rain. Yeah, it's like literally the rain on another planet.
Yeah, exactly. Yeah. Or even like a whole star.
Or a whole star, yeah. So in the meantime, we're looking for like that rare, what might be the rare jewel of the actual universe, and maybe that's life. But then on Earth, we've been willing to trade life for those diamonds. So something to think about, maybe in terms of a space perspective, in terms of value.
But you know what? I think it also makes sense and poetic why usually if you were to go for engagement ring, you go for the diamond. Great selling point.
Maybe instead it should be just like I don't know, what would be better? Like a meteorite ring? I don't know.
Oh yeah.
That'd be neat. But yeah, here we go. We're looking at Saturn. It's one of my favorite planets to look at. You might have noticed that what I had to do is I've changed the mode in which we are looking. So
can you make it bigger? Can you zoom in?
I can zoom a little bit more. It is a wee bit fuzzy, so I don't want to zoom in too much because we're going to lose a little bit more definition. Planets are notoriously hard to actually take pictures of. And you might wonder, well, how is that? I've seen all kinds of clear photos of planets. There are special methods in order to do that. One of them is called lucky imaging. So what happens in lucky imaging is you actually video record the planet, which is kind of what we're doing right now. This is sort of like a low-speed video of the planet. Each frame is 11.6 milliseconds we're doing right now. But if you take an image or a video like that, lucky imaging will look through all the individual frames for the ones that happen to be in focus, because the motion of the atmosphere, and planets are actually really tiny in the sky compared to some of the other things we've looked at. The motion of the atmosphere makes it look like it's waving around like it's in water. So lucky imaging will take those few lucky frames where it happens to be in focus and take them out and stick them together so that you have an in-focus image of the planet. Whereas right now we're kind of looking through a wavy atmosphere, why it tends to be a little bit fuzzier looking.
And also Saturn, the only way we see it is its reflection. The light is reflected from the sun because planets don't give out its own light.
Totally.
That's another reason.
Yeah.
Oh, yeah, go ahead.
Oh, I was going to say, and right now there's some speculation that there might actually be a ninth planet in the solar system, but that it's so far away.
Pluto? Is it not Pluto?
No, it's not Pluto. I mean, I heard it's honorarily a planet at the Trottier Observatory.
That's the argumentative. Sure.
Yeah. But if there were a planet that's really far out there that is part of the solar system, for the reason you said, if planets are reflecting light, if there is one really far away from the sun, it's not going to be it's not going to be reflecting a lot of light, so it's harder to see.
Yes. I just remember something. So Saturn, did you know that the day Saturday was named after Saturn?
No way. What?
Yeah, so I'm now curious what happened on the Saturday? So maybe Saturn was discovered on a Saturday? Is that what it is? They just have to call it Saturday?
I don't know. If any one of you knows out there, put it in the chat. We want to know.
Saturday named after Saturn. Even though it is not Saturday. Oh well.
Yeah, no. Saturn, great planet. Well, how much longer do those rings have?
The rings?
Yeah, I heard they're leaving. They're like going away.
Yeah, I think 100 million years from now.
I'll put it in my calendar.
Put it in your will.
Put it in my will, yeah. I don't know if there's much difference there, but yeah.
And then also put in the will for your grandkids. Put it in the will for your great-great-grandkids. So together, tell them to put it in the will.
I think there's more greats that have to be added to that in that will.
Yes. Actually, you know what's also mind-blowing about Saturn? So Saturn is denser than water. So if we had
Crazy.
an ocean that would just larger than Saturn itself, it would be just floating. Saturn would be floating on water.
Amazing. Isn't that cool? That is so cool. It's Jupiter. Look, we got Jupiter here.
Oh, we already switched to Jupiter?
Yeah.
I can't see it, but
I think about rotating over, so yeah. I wonder if, let's see.
I wonder, are we facing the red spot?
We might be.
Not.
No, probably not. Let's see. Is it this one?
Would be cool. Or there was a time when you can actually see the moon shadow on the planet.
That happens sometimes, yeah. So what causes that?
The moon shadow?
Yeah.
Because in front of it?
Yeah, so yeah, well, sometimes actually we see one of the moons sort of right here. Actually, if I blow the exposure out a little bit, we'll see. So there is a moon here, kind of one of the Galilean moons around Jupiter. So if I overexpose Jupiter, you'll see it there. There's one of them. So if that moon were to happen to pass in front of our view of Jupiter, it does leave a shadow on Jupiter, and sometimes we can see them. These transits, we call them, of the moons.
Very bright.
Yeah. There's another one over there. Actually, if I zoom this all the way back, we could probably see all four of the Galilean moons, at least 3.
Did you know there are 95 moons on Jupiter?
Is that the count we're up to now? That's amazing.
Yes, that's what it is now. Maybe it's more. I think it's gonna go up to 100 at some point.
Well, I mean, Saturn's over like up to 180 or so. Even on this exposure here, we can see the stripes on Jupiter. Ever so slightly, you can see them from Jupiter's fast rotation. Jupiter rotates faster than any planet in the solar system and creates basically a churn in the atmosphere where some of the lower, heavier elements in the lower parts of the atmosphere will be churned up to the surface, and we get that coloring on Jupiter.
Nice. It's also the oldest planet in our solar system.
Yeah, likely formed first, yeah.
Actually, Jupiter itself, it's its own solar system.
Yeah, kind of.
And the largest moon, which one? What's the largest moon of Jupiter?
Ganymede.
Ganymede, and it's larger than Mercury.
That's crazy.
Mercury is our planet. So one of those moons could have a life. You never know. Maybe there's a civilization in one of those moons.
Yeah, or at least some like space plankton or fungus or something. In fact, one of the moons, Europa, we know has a subsurface ocean. And we've sent a probe there recently called JUICE that's supposed to be scanning that surface. We're looking to, in the future, put something inside of that moon to see if there might be anything alive. And that moon, Europa, which is just one of some of the watery moons around the gas giant planets, has twice as much water as Earth. Imagine that. Just we think of ourselves.
Or ice? Or is it
it's
small?
It's both. Yeah, there's ice on the surface, kind of encasing the outer part like a glacier, and underneath there's an ocean. That ocean could be 10 times deeper than Earth's ocean, which is nuts.
That is crazy.
Yeah.
I was just thinking, I sometimes try to think about, how far away a planet, and Jupiter is one of the interesting planets because it can be its own solar system. So I'm just thinking if we were to travel to Jupiter. So Jupiter is about 520 million kilometer away. So if we were to drive to Jupiter, how much, like if we were to drive, so let's just say we're driving with a car, maybe 100 kilometers per hour. How long do you think it will take us to get to Jupiter from Earth?
At like highway speed, if there was a road that long, I have no idea. How long would that take?
About 600 years.
600 years. Wow, pack enough snacks for that trip.
600, if it, yeah, that's just so 100 kilometers per hour. If you drive 100 kilometers per hour, it will take you about 600 years.
Oh my goodness.
Plus or minus few years.
And you'd have to hold your breath the entire way. Worst road trip ever.
It will be very, very dark road trip.
Speaking of road trips into space, there is one place, and I think we'll end off our tour of space there, that's much closer to planet Earth, and that we are planning to return to in the very near future, and that is our closest neighbor, the moon. So that's where we're going to go to next.
Yay! I actually have, what do you call it? I have a land. I claimed a land on the moon. I don't know how true. Because someone, like, you know, those, I don't know, there's those where you can buy a star or name it after yourself. So when you buy a star, you also get some land, or I don't know how many, was it like 10 acres on the moon?
Yeah.
I was like, oh, that's wonderful. Just in case climate change completely, or global warming destroys Earth, I have some place I can build up my cottage.
Yeah.
I just have to figure out how to get to the moon.
That's cool.
And how to breathe on the moon. And also the gravity. So the gravity on the moon is actually 6 times, I would say 6 times less or weaker than Earth.
Yeah, so that's why you're floating around so much.
So you can actually jump higher, 6 times higher.
That's nuts.
On the moon. Which would be cool. Yes. I can jump higher. That's actually very cool. Cool thing to think about.
Now, we're kind of staring at a sort of just flat... The thing about the moon right now is that it's almost full. And so when you think of a full moon, the light from the sun is shining directly on it, right from above. So like if you were standing on the moon's surface like we're looking at right now, the sun would kind of be straight above you, which means we don't get a lot of shadow on the moon like this. And so the moon kind of appears sort of flat. What I'm going to do is try to move us to a part of the moon that seems a little bit more interesting. So let's I
think I'm not sure Joanna's serious. Or is she telling a joke? Did you hear about the new restaurant on the moon? It's got great food, but no atmosphere.
No atmosphere. That's fantastic. All right, let's see here. Okay, we'll bring up the manual controls for the telescope. We're gonna move around on the moon's surface here and see if we can get more, maybe toward an edge, so we can see more of that cool stuff there. Oh yeah, look at that.
Oh, there's Tim Hortons at 300 years.
In the future, yeah, that might very well be the case. Who knows? But yeah, for those of you who don't know, we are returning to the moon, and we're going next year. So we've already sent a mission to the moon last November called Artemis 1. If you remember, the last time we went to the moon, it was called Apollo. If you know your Greek mythology, Artemis is Apollo's sister, and that was intentional because last time we went to the moon was just a bunch of American dudes. And this time we're sending a much more diverse group of people, men and women and people from all over the world, 15 different countries, to return to the moon's surface. Artemis 2, which is launching next year, will not be landing on the moon, but we will be circling the moon with a set of astronauts, and we will be finally landing on the moon's surface in Artemis 3, which is scheduled for 2025. And I'll show you the crew that's going. We have a Canadian astronaut that's heading up there next year. So if you don't already know about this, Canada is participating in this mission because we are providing a third generation of Canada's robotic arms, which is cool.
Very
to a new space station that's going to be going around the moon called Gateway Station. So this is here. This is Jeremy Hansen. Let's get his space.com photo here. This is him here. And I don't know about you, but I think Jeremy Hansen was selected for this mission because he looks like a real life version of Buzz Lightyear. Tell me that that doesn't look like Buzz Lightyear. He has a Buzz Lightyear chin.
I don't know. We need to bring Buzz Lightyear. Put them right side by side. And we can make the comparison.
We can make the comparison then, yeah. But we have a whole new group of people going back to the moon. This is pretty cool. You probably can't tell because this is a live feed that only has audio but not video. But I wasn't old enough to be around for the last moon landing, so I'm very excited that we're going to be around for this moon landing. And the place in particular that we're going to the moon this time is actually the lunar South Pole. And the reason why we're headed there is because craters at the South Pole are permanently shadowed, so the light hits more toward the horizon. And we have found water ice in those craters. So there's actually ice on the moon inside of these craters, and that's one of the reasons why we're going to those new regions on
How
the
come
moon.
we've never known that before? Like we've been on, not us being on the moon, but we've always studied the moon. How come we've never known this? Why are we knowing about this now?
That is a great question, Zena. I'm not sure if we've ever had something in an orbit quite that reaches the southern lunar South Pole. Someone in the chat, if you happen to know this. But because we had satellite imagery and spectrographic readings of the lunar South Pole, we determined that there was ice there. And then, just recently, India landed on the moon, which makes it the fourth country in history to get something on the moon's surface with their Chandrayaan rover, and it also confirmed that there is water signatures at the South Pole of the moon, as well as sulfur and a couple other interesting things there as well. So that's one of the reasons why we want to go back and check out this place. And if we have water on the moon, that means we might be able to use it to stay there longer. One of the disadvantages in going last time is we could only stay for a little while, but if we have water and we're building a space station, maybe we can send people there longer, up to 3 months. We're hoping to at a time.
That will be interesting.
Right?
Knowing that we can have an atmosphere, but I guess we can create an atmosphere if we have water.
Yeah, and we can also use that water and separate it into its components, hydrogen and helium, for rocket fuel, which is pretty cool too. I'm just going to slew across to the other side of the moon, and then maybe we'll wrap up. Give me a few extra minutes, because I know we started late there.
Did you know it has that orange color? I don't know. I don't think we have forest fire.
No, you know what this is? This is actually color correction that we would have to do to the camera. And
okay.
I don't recall if I'm not in live stack mode. This is me showing my rustiness from last time I did this. If I'm not in live stack mode, how do I get the color correction in the histogram? Let's see.
Because I don't remember it being this reddish color.
Histogram. Can I do it like this? Aha! Nope. If I go logarithmic.
Very nice.
No. Okay. That's not quite it. I don't quite recall. What if I go live stack, but just turn the stacks down really low?
Someone's asking, is there a bunny on the moon? I don't know.
A rabbit on the moon? Yeah.
We're not talking about the dust bunnies. If it's a pun, I don't know.
No, I don't think that's the way we're supposed to do this. Anyways, there is, you are right. The color is not quite right. There is a way to adjust it, but I don't remember how to do it in live feed mode. But yeah, it looks a little bit reddish from what we want it to look. Here, let me see if I can clear this up for 1 second here.
If you were given the choice to go live on the moon, like they just say they build a satellite or a hotel, would you go?
Oh, I would totally go. Yeah. Well, you know what? Let me qualify that question. I would go to space. I would take up space in space if it meant that I had the training to contribute to exploration.
Okay.
In other words, I don't want to go just as a tourist. I would want to go because it's advancing scientific knowledge.
Nice. Well, if you're going as a tourist, you have to pay the money for it.
That's the other problem. So it's not like I can afford that anyway.
Unless you're Elon Musk, that's a different story.
Yeah, or if I have wealthy friends. But no, although if you want to find a cheaper alternative, still not like super cheap, but there is also flights on the zero G airplane, which simulates microgravity that you can do as well. So that's another possibility. Those flights are still like $10,000, but it's a lot cheaper than going to space,
Oh my God, let me pay off my mortgage first.
right? Yeah. Let's get to the other side of the moon here, and then we'll.
But you know what? If it's only $10,000, that's actually nothing for Vancouver. $10,000, nothing in Vancouver.
Well, yeah, it depends. I mean, for me, that's like almost a year of rent. But I hear what you're saying. All right, so we'll probably wrap up there. Got one other thing to note. Okay, so on October the 14th, speaking of the moon, is it October the 14th? Make sure I got my dates right.
October 14th? What date is that? Let's see.
Is it October the 14th? It is October the 14th. So on October the 14th, there is an annular solar eclipse going on. So it's not a total solar eclipse, but the moon will be passing in front of the sun. And we won't see the total eclipse, or even the total annular eclipse from here. But from BC, we will see the moon approaching and covering part of the sun. And we're going to have a special event at SFU Trottier Observatory for that. We'll be making more announcements about it. But keep an eye and ear out for that. So if you're a space nerd and you want to come out and hang out with us at the observatory, we will be watching the event and seeing the moon pass in front of the sun. And you know what? I just want to let people know about this. It is amazing that we even have eclipses at all. The next total solar eclipse is happening April 8th of 2024. It will pass over eastern parts of Canada, including Montreal. Now, we just happen to live in a time in history when our moon just happens to be exactly the same size as the sun in the sky, covering it in such a way where you can actually see the atmosphere of the sun. And that's nuts. Now, there might be planets like ours out there, but we might be one of the few places in the entire universe where that just happens to be, where our moon and our sun just happen to be the same size in the sky. So when kids ask me at the planetarium and at the observatory up at SFU whether or not I think aliens visit Earth, I'll tell them I'm not sure, but if they were to come here, they might be as tourists to see solar eclipses. So that's why we should take advantage of them, and you should too. So make sure you come out October the 14th, hang out with us, and then April 8th, 2014, go out to Montreal and go watch that total solar eclipse.
So are you going then?
I might go. The other place I might go is Texas. Not that, Texas is not exactly a destination these days, but what I'll say is that it is one of the clearest sky locations probably for that eclipse. And I think some people might be gathering in Texas on April 8th, 2014 to try to see that. So that's another possibility too.
I'm excited for it.
Yeah.
I've actually never seen an annular eclipse, so I'm excited for that one.
Yeah, it's cool. So we'll have some tools set up here. We're going to give everyone glasses. So we got glasses that we're trying to order. You'll be able to come up, get some glasses to protect your eyes. Don't look at the sun, without those, because that's a bad thing to do. So we'll have those available for us as well. So make sure you come out October 14th up here in the morning. Annular eclipse. We'll have glasses. We'll be able to look out to hang out together and watch this celestial event as living stardust on our planet, and that's pretty awesome.
Very, very, very cool.
Zena, I'm so glad that we got to do this together. Thank you so much for hanging out with me and talking about space.
You too. So glad we got to do this. It was the very first one.
Yeah. And thanks to all of you out there in the world for connecting in with us. 71 people watching live right now. That's amazing. Thank you so much, all of you. We love you all. If you can come in person, remember we're still doing Starry Nights every clear Friday up at the Trottier Observatory at SFU. The last Friday every month we're doing the stream, so if you're out of town or can't make it, you can always tune in then. Share the news, let people know around the world. That can always come in where we try to make the stars a little bit closer to all of you. Everyone out there, have a great night. Remember to keep looking up, and we'll see you at the next Starry Nights.
And just to thank our moderators, thank you to Abby and Rohit and Michael for answering any questions on the chat. We appreciate you.